I have had the chance to work on a wide range of applications of low-temperature plasmas, and I have always been fascinated by the very rich underlying physics of these plasmas. In this talk, I will discuss the aspects of low-temperature plasmas that I find most intriguing, particularly their nonlinearity and complexity. These properties lead to the formation of self-organized dynamic structures, which are present in many conditions and applications. This is the outline of my talk. In the introduction, I will say a few words about my contributions to the field, and about the evolution of research and application topics in low-temperature plasmas over the years. In the second part, I will recall some examples of pattern formation and self-organization and illustrate the different approaches in modeling of these plasmas. And in the third part, I will discuss in more details two examples of self-organization that I have been working on more recently: the formation of moving striations in positive columns, which is a very old problem, and the question of instabilities in magnetized plasmas. Since I got this prestigious prize, I feel a little bit obliged to introduce myself by saying something about my work and my contribution to the field along the years. As I said, I have been working on different applications of low-temperature plasmas. Most of them are listed here. In these different applications, I was interested in trying to answer basic physics questions with the help of modeling and simulation. The plasmas of ion sources for satellite propulsion are magnetized. There are instabilities in a large range of frequencies and wavelengths in these plasmas. With my group, we clarified the physics of some of these instabilities in Hall thrusters and magnetron discharges. Negative ion sources for the ITER neutral beam injection system are also low-pressure magnetized plasma, and we studied charged particle transport, hydrogen chemistry, and neutral depletion. We showed the consequences of the Hall effect on the plasma properties. Surface dielectric barrier discharges can be used as actuators for flow control. We studied the mechanisms of plasma flow interaction in these actuators, and particularly the roles of surface streamers, and of ion wind in this interaction. We developed simple models to explain the formation of filamentary patterns during microwave breakdown at atmospheric pressure that were observed in experiments. Microdischarges and microplasmas were used in plasma display panels. The research on plasma display panels became very important during about 10 years, starting in the mid-1990s. We developed the first simulation tools to understand and optimize the discharge efficiency. These tools were used by several companies in Europe, Japan, and Korea. We also studied self-organization in dielectric barrier discharges and the physics of plasma jets, also called plasma bullets. We showed that the word guided streamers was more appropriate. We were involved in other applications like plasma switches, gas discharge lasers, plasma processing, and dusty plasmas. My modeling approach was to develop models as simple as possible while still capturing the essential aspects of the problem, and to have a good balance between accuracy and simplicity. There is a quote attributed to Einstein that says, "Everything should be made as simple as possible, but not simpler." Interpretation of the model results is probably the most difficult part of modeling. This enables insight and understanding, validation and verification, hypothesis testing, and theory development. Interpretation of the results requires the development of a complementary theory. For example, when one wants to understand the mechanisms responsible for the development of instabilities predicted by the model, one needs to perform a perturbation analysis by linearizing the equations. I believe that finding an effective means of visualizing the results of a model is a crucial aspect of modeling. It not only aids in the interpretation of the results, but also enhances our understanding and facilitates their explanation and communication. The primary goal of the models is to understand the underlying principles, guiding experiments, and optimization. However, building predictive models for complex systems like Hall thrusters remains a challenging task even after years of research. The range of applications of low-temperature plasmas is quite impressive. In this slide, I am going to show the evolution over the years of the percentage of publications of the low-temperature plasma community on different application topics. The data includes both research and applications articles, and the plot is on a logarithmic scale. Plasma processing of semiconductors is one of the most important topics and has constantly grown since the 1980s. Research on dusty plasma emerged in the 1990s when it was discovered that dust particles can form during plasma etching or deposition. This led to significant interest in the theoretical study of dusty plasmas, such as the exploration of dusty plasma crystals, and to important applications like nanoparticle synthesis. This research topic remains very active. Plasma display panels became a hot topic in the mid-1990s, particularly in Japan and Korea. However, the interest in plasma display panels decreased with the development of large LCD, LED and OLED displays. Research on plasma medicine became important around 2000 and has since experienced rapid growth. The number of published papers on plasma actuators for flow control or combustion control increased abruptly around 2005. This field continues to be active. Gas conversion, related to pollution control and greenhouse effects, emerged as an important research topic approximately 10 years ago and is experiencing significant growth. Research on plasma agriculture started slightly later but is also in rapid expansion. The investigation of plasma thrusters for satellite propulsion started a long time ago and remains an active research area. So, from this plot, we see that our field is very active. A new research topic has emerged about every 5 years. I am curious to see if new research topics will continue to appear at this rate. Now I am going to talk about self-organized structures and complexity in low-temperature plasmas. Instabilities and self-organization are ubiquitous in low-temperature plasmas. This is due to the complex and nonlinear interplay between charged particle transport, ionization of neutrals, and charged particle losses. Neutral transport, gas heating, and neutral depletion can also be a cause of instabilities. Of course, plasma chemistry can contribute. The large variety of conditions leads to different forms of instabilities and self-organization. Gas pressure can vary from a fraction of Pascal to atmospheric. There are many ways of generating the plasma. The nature of the gas is also an important parameter. More generally, low-temperature plasmas are far from equilibrium systems exchanging energy and momentum with the surroundings. These are the conditions of dissipative structures, as defined by Prigogine, and the keywords of dissipative structures are self-organization, complexity, and emergence. This is Ilya Prigogine, the Nobel Prize in Chemistry, not to be confused with another Prigogine. This slide shows examples of self-organized structures in low-temperature plasmas. On the left, we have discharges on a dielectric surface that are called Lichtenberg figures. The middle figure is a network of filaments formed in a microwave discharge. The microwave field is below breakdown, but the field is enhanced and above breakdown near the two metallic rods. The discharge starts on the two metallic rods and forms a network of filaments that expands into region where the electric field is below the breakdown field. On the right we have some experiments of microwave breakdown in air at atmospheric pressure. This experiment was done at MIT and is reported in this paper. Here the microwave beam is focused on a point. A plasma filament parallel to the electric field forms at this point. This filament absorbs and reflects the microwave beam, leading to the formation of standing waves in front of the filament, with maxima and minima of the electric field. The black and white pictures are integrated in time. This is a 2D simulation of the experiment in a plane containing the wave vector and the electric field of the microwave. The structures that we see are microwave streamers that form in front of each other, due to diffusion and ionization in the enhanced electric field of the standing wave. Here the simulation is performed in a plane containing the magnetic field. The filaments are perpendicular to the simulation plane. We see the formation of a complex filamentary patterns that seems to move in the direction of the microwave source like in the experiments. This was done with a very simple model coupling Maxwell's equations with a basic fluid model of the plasma. But this model was able to reproduce and explain the observation. Dielectric barrier discharges are famous examples of discharges that can lead to self-organized static or dynamic patterns that are typical of reaction-diffusion systems. Here the conditions are a pressure on the order of 100 to 200 torr in a noble gas, with a 2 mm gas gap and 2 mm dielectric thickness. By changing the conditions of gas, pressure, voltage amplitude or frequency, we can obtain hexagonal filamentary structures, a labyrinth structure, a mixture of single filaments and uniform regions, targets, apparently uniform plasmas, and rotating spirals. We understand only some aspects of the self-organization of these filaments. Some 3D commercial models of glow discharges are now available, but I am not aware of modeling papers reporting the large variety of structures that can be found in experiments. The filaments can appear as immobile or exhibit some dynamical properties like in this movie. This is a quasi-hexagonal structure, and we see different types of events like filament generation, annihilation of filaments and merging of filaments. The well-known plasma ball is even more complicated. This is a dielectric barrier discharge between a central electrode and the surroundings. Clearly there is a coupling here between plasma filaments and gas dynamics since we see an upward motion, due to convection induced by gas heating. There have been some attempts at describing and understanding this system, but we are still far from this goal and there is no model able to describe this. Instabilities and self-organization are also ubiquitous in magnetized plasmas such as those of magnetron discharges, or Hall thrusters for space propulsion. In these plasmas an external magnetic field is placed perpendicular to the discharge current or to the applied electric field. This is a so-called E cross B situation where there is a large electron current in the azimuthal direction. That can lead to charge separation and to the formation of rotating non-uniformities. And finally, everybody knows about the formation of moving or static striations in a positive column plasma. The phenomenon of stratification of a low-temperature plasma column has been known since Faraday. The striations can form in a variety of conditions depending on the gas, current, pressure, tube radius. Different mechanisms can be responsible for stratification, and they are still not fully understood. There are different levels of modeling the nonlinearity and complexity in low-temperature plasmas. We have the kinetic models which are often based on particle-in-cell simulations with Monte Carlo collisions. There are fluid models which imply assumptions on the particle distribution functions. I will show examples of kinetic and fluid approaches in the next section. There are also phenomenological models which are not based on the fully detailed physics but on more macroscopic properties of the system, which can be based on results from finer models, or which can be data-driven. Phenomenological models are needed to describe large-scale complex systems. For example, it is possible to simulate a single streamer with fluid or kinetic models, but these models cannot be used to describe Lichtenberg figures or a complex system of branching streamers. I am going to take an example of phenomenological model in another field. This is the simulation of pedestrian motion. To do so we do not need to know what is in the mind of each individual pedestrian. We only need a few characteristics of the individuals. There is a famous model called the social force model. This model is based on a few assumptions on people in the crowd. They have an overall goal, which may be to exit a building or to follow signs. They cannot walk through walls or other solid obstacles. They have an individual or cultural view on how close they may want to be to strangers. They will have a certain amount of randomness in their movements. Putting these assumptions in a mathematical form, one can simulate some aspects of the motion of pedestrians. This is an experiment on two groups of people crossing each other in a corridor. Pedestrians coming from the left are in black, those coming from the right are in red. Very soon, each group forms separated lines. This experiment is very well reproduced by a simulation based on the social force model shown on this movie. Here the two groups are represented by the blue and red circles. As in the experiment, we see the formation of lines in each group of pedestrians. Now I come back to low-temperature plasmas, and I take the example of a phenomenological model of Lichtenberg figures. This is a simulation of a surface discharge described in this paper in Physical Review Letters almost 40 years ago. The model developed by these authors is extremely simple. The principles of this model are shown here. This is a two-dimensional model where the electric potential is set to 0 in the center and to 1 on the external circle boundary. Filaments form on a rectangular grid. The discharge starts in the center with a filament in a random direction. Filaments are supposed to be equipotential, meaning a very large plasma conductivity, so they are at 0 potential. At each time step, a new filament forms from the tip of a previous branch with a probability proportional to the potential between the tip and neighbor grid points. Poisson's equation is solved after each time step. The probability law of branching can be adjusted by comparing the fractal dimension of the computed figure with the experimental one. This model is obviously too simple because it assumes infinite conductivity of the branches. Also, all the branches have the same length, and the branching occurs at 90 degrees on a rectangular grid. These assumptions can be improved based on the knowledge deduced from detailed fluid models of a streamer. This has been done in this interesting paper by Luque and Ebert. This is a three-dimensional model of growing discharge trees. I will still call this model phenomenological, but it contains much more detailed physics deduced from the simulations of individual streamers. Contrary to the previous model, the plasma conductivity is finite. The model includes a self-consistent charge transport model with some physical laws of charge conservation. The model can predict streamer branching angles, charge structure within the streamer trees, and streamer reconnection. And what is interesting is that the collective dynamics exhibits some features that cannot be derived from microscopic models. A 3D model of branching based on the full fluid equations plus photoionization that has been recently published. But I believe that there will always be some levels of complexity that can be described only by phenomenological models. Another type of phenomenological model is illustrated by the work of the group of Professor Perwins at the University of Munster. They tried to represent DC discharges, or dielectric barrier discharges, by a distributed equivalent circuit where the elements are nonlinear. This can be put in the form of a reaction diffusion system where the functions U, V, W are current densities and voltages depending on two dimensions. This is an interesting approach because reaction diffusion systems can be analyzed mathematically. Professor Perwins and his group applied this approach to DC discharges. We try to extend this to dielectric barrier discharges without real success yet, but I think this approach could lead to a better understanding of the large variety of patterns that are observed under some conditions in DBDs. The examples of complexity in low-temperature plasmas that I just gave are relatively simple compared with some problems in real applications, for example in plasma processing or Hall thrusters. I believe that the future approach to develop predictive models will be based not only on input from basic physics, but also on big data or large data acquisition from plasma diagnostics, machine learning, and artificial intelligence. This is clearly an extension of phenomenological models. There are interesting papers listed here for plasma processing, Hall thrusters, and plasma medicine. Now I want to come back to kinetic and fluid models and show how they can help us understand the nonlinear physics of low-temperature plasmas. I will discuss two examples. The first one is about positive column striations, and the second one is about rotating non-uniformities in magnetron discharges. First, positive column striations. We want to understand the formation and dynamics of these striations with a simple one-dimensional model. If we consider that the plasma is quasi-neutral, we can write this simple ambipolar diffusion equation with ionization. The Laplacian term can be split into an axial component and a radial component. We can put the radial component on the right-hand side of the equation, so we get this expression. In the axially uniform and steady-state regime of the positive column, the left-hand side is zero and ionization must balance the ambipolar losses to the walls. The radial profile is a Bessel function. We can define NUW as the frequency due to ambipolar losses, and we get this simple one-dimensional axial equation for the positive column where the ionization frequency depends on the electric field and the loss frequency is given. This is a one-dimensional reaction diffusion equation. We also need to write an energy equation for the electrons because the ionization frequency and ambipolar diffusion coefficient depend on electron temperature. To look for possible instabilities, we do a perturbation in plasma density and electron temperature. We linearize the equations with respect to this small wave perturbation of the form written here. Omega is the complex frequency, k is the wave number. Little omega is the real part of the frequency and gamma the imaginary part. Gamma is the growth rate of the perturbation and there is an exponential growth of the perturbation if gamma is positive and the system is not stable. The perturbation is damped if gamma is negative. Injecting these perturbed expressions of the density and electron temperature in the continuity and energy equations, it is easy to obtain the expression of the frequency and growth rate gamma as a function of wave number. This is a dispersion relation. I am not going into the details. One gets this expression for the growth rate. In this expression, the first term is related to axial ambipolar diffusion, and it is negative. As expected, diffusion is a damping term. The second term is proportional to the derivative of the ionization frequency with respect to electron density. This term is zero if ionization is only due to direct ionization of the neutrals. It can be positive and non-zero in the case of stepwise ionization. This can trigger instabilities. But it is known that striations can be present in rare gases at low current density, when only direction ionization is present. I will suppose that there is no stepwise ionization. The question is, what is the mechanism? The system is unstable only if the third term on the right-hand side is sufficiently positive. The derivative of ionization frequency with electron temperature is positive. So, to have a positive growth rate, the term delta T over delta Ne must be positive. That means that the perturbation in temperature must increase with the perturbation in density. To check this, we need to write an energy equation. I will come back to the energy equation later. I want first to show how a particle simulation can handle this problem. The idea is to build a simple one-dimensional particle in-cell simulation with Monte Carlo collisions that can describe the stratification of the column. We consider an initially uniform with a given plasma density of a given length, and we assume periodic boundary conditions. We impose the average electric field in the column. Imposing the column field is equivalent to fixing the tube radius. This field is related to the fact that ionization must balance the radial losses of charged particles. The total axial field in the column will therefore be the sum of the applied field E0 plus the space charge field obtained from Poisson's equation. In the Monte Carlo module, ionization is treated as usual. Each time an ionization occurs, we generate an electron-ion pair at the location of ionization, but we also remove randomly another electron-ion pair in the simulation. This represents the fact that the wall losses are balanced by ionization. Doing so, the number of charged particles in the simulation does not change, so the average plasma density does not change. This is a very simple one-dimensional particle-in-cell model. The simulation can run very quickly on a desktop computer. Of course, it can be made more complicated in 2 dimensions or even 3 dimensions. But one would not get much more information. As I said, I think that a model must be adapted to the problem, and that unnecessary complications should be avoided. Here are some results from the particle-in-cell simulation for a positive column in neon at 1 torr. The column length is 6 cm and the applied field is 6 volt per centimeter. We start with a uniform plasma density, but after a few microseconds, we obtain these structures which look very much like a moving striation. The blue and cyan curves are the ion density and electron density along the column. The red curve is the electric field, which is the sum of the applied field plus the space charge electric field. The striations move to the left. Since the applied field is negative, this is the direction toward the cathode. Here we see, at a given time, the space variations of the electron and ion density, electric field, electron temperature in green here, and ionization rate. The electron temperature is slightly modulated while the ionization rate is strongly modulated. That means that the tail of the electron energy distribution function is much more modulated than the bulk. So, the simulation gives something which looks very much like the moving striations that can be seen in experiments. The particle-in-cell Monte Carlo collisions model reproduces the growth of the instability and its saturation, and provides the detailed kinetic properties of the instability in the saturated regime. For example, the potential drop between striations is quantified and is related to the excitation and ionization thresholds, in the case of rare gases. This is consistent with theory, Sending, Galabowski, and co-workers, and with experiments. But the simulations do not provide a clear explanation of the mechanism responsible for the instability. To understand why the positive column is not stable in these conditions, we need to do a linear analysis of the equations. We come back to the fluid equations. We have seen the continuity equation where gamma is the electron flux defined by this ambipolar diffusion term proportional to the density gradient. One can also write an energy equation with an energy flux H. The energy flux has a term proportional to the temperature gradient. This is the well-known thermal conductivity term. On the right-hand side, we have a first term related to Joule heating and a second term related to energy losses due to collisions, mainly inelastic collision with neutrals. The energy loss per unit time L epsilon is a function of the electric field, just like the ionization frequency NUI. They both increase with the electric field. The constant terms gamma 0 and H0 correspond to the fact that there is an electron current in the column. The energy flux is often written like this in the fluid models. But more accurately, there is another term proportional to the electron density gradient with a coefficient which is called the Dufour coefficient chi. Chi is related to the difference between the diffusion coefficient in energy and the diffusion coefficient in space. For a Maxwellian distribution, chi is 0. This is the reason why it is often neglected. But the electron velocity distribution in a positive column in noble gases is far from a Maxwellian, so chi is non-zero. Now we can linearize the continuity equation and the energy equation. I am not going into the details of the derivation, but this is not very complicated. We have seen already that the continuity equation gives the growth rate of the perturbation gamma, with a negative, damping term, and a second term which is proportional to delta T over delta NE. This ratio can be deduced from the linearized energy equation is given by this expression. To have an instability, the growth rate gamma must be positive, so that delta Te over delta Ne must be positive. In this ratio, the energy loss term L is positive, its derivative is also positive, and the thermal diffusion term is positive. So, the only way for this ratio to be positive is that chi E0 is negative. It turns out that the Dufour coefficient can indeed be negative in rare gases. The Dufour coefficient can be negative because the diffusion coefficient in energy is significantly smaller than the diffusion coefficient in space. This is shown on this plot obtained from solution of the Boltzmann equation in a uniform field with Boltzig plus in argon. This is due to the special shape of the electron energy distribution function, which is far from a Maxwellian. The kinetic model reproduces the instability but does not explain it. The linear analysis of the fluid equations allows to understand the reasons for the instability. However, in the saturation regime, the nature of the instability is kinetic, and its description requires a kinetic model like the particle in-cell simulation. Just for references, there have been many papers on this topic since the 1960s by different authors. Important papers by Tsending, Golubarsky E. But the role of the Dufour coefficient in the triggering of this instability has been first suggested in this paper by Miles Turner and co-workers in 2005 in the context of a cylindrical inductively coupled plasma. A more recent study in the same context has been performed by these people. And the connection with positive column striations with a combination of fluid and kinetic approaches can be found in this paper published last year in Physics of Plasmas. Last example of instabilities and self-organization in a low-temperature plasma. I consider now the magnetized plasma of a magnetron discharge. A magnetron discharge is like a glow discharge that can operate at low pressure in the millitorr range. At these low pressures, an external magnetic field is used to confine the electrons in the gap. The magnetic field is perpendicular to the electric field in this region. In this configuration of electric and magnetic field, there is a large electron drift in the E cross B direction, which is the azimuthal direction. So, electrons are rotating in the azimuthal direction, and their motion toward the anode is strongly reduced by the magnetic field. The ions are much less sensitive to the magnetic field because they are much heavier. So, they do not rotate in the azimuthal direction. The large difference between the azimuthal electron and ion velocities can induce charge separation and can be the source of instabilities. Here are some examples of rotating instabilities. The plasma is not uniform in the azimuthal direction. These non-uniformities rotate in the azimuthal direction at a velocity of several kilometers per second. They are called rotating spokes. One can have one or several modes depending on the conditions of pressure or magnetic field. There have been a lot of measurements on these spokes. Some space and time resolved probe measurements show very large azimuthal oscillations of plasma density and electron potential in the spokes. For example, these are some probe measurements by Julian Held and co-workers at the University of Bochum. The probe is placed in the plasma, about 1 centimeter above the cathode. In these conditions, they see one spoke moving in the -E cross B direction. The time evolution of the plasma density, electron temperature, and electric potential are shown here. We see that when the spoke reaches the probe, there is a huge increase of the plasma density, a very large peak of electron temperature, and a very sharp increase of the electric potential. There is a potential drop of more than 60 volts at the front of the spoke, and the electron temperature increases from about 5 eV to 20 eV just in the leading edge of the spoke. The electron energy distribution has also been measured. The tail of the distribution exhibits a large modulation at the spoke front. So how to model this? A three-dimensional particle simulation is too expensive in terms of computation time. So, we chose to do a two-dimensional simulation. We know that the E cross B current in the azimuthal direction is the main source of instabilities in these types of plasmas. Therefore, the azimuthal direction must be included in the simulation domain. So, we consider an axial azimuthal simulation domain. This is the axial direction between cathode and anode. This is the azimuthal direction. This is a rectangular domain, but we assume periodic boundary conditions in the azimuthal direction to describe the fact that this direction is closed on itself. The magnetic field is maximum on the cathode surface and decreases to about 0 on the anode. The magnetic field is perpendicular to the simulation domain and the E cross B direction is directed downward. We use conditions similar to the experiments. Argon at 0.6 Pascal, applied voltage between cathode and anode of 260 volts, gap length 2 cm and azimuthal length 8 cm. This is like a glow discharge except for the magnetic field and the much lower pressure. First, I want to show what the particle simulation would give for a standard glow discharge without magnetic field at a higher pressure. These plots are contours of constant ion density, plasma potential, electron temperature, and ionization rate. The plasma is perfectly uniform in the azimuthal direction. There is no instability. We can plot the axial distribution of these quantities. And we recognize the classical structure of a DC glow discharge with a cathode sheath and negative glow. We see the large potential drop in the cathode sheath and quasi-constant electric potential in the negative glow. Electrons gain energy in the sheath as we can see in the plot of electron temperature here. And they release this energy by excitation and ionization in the glow with a maximum at the entrance of the negative glow, as we can see on the right plot. Now the particle in-cell simulation with a magnetic field decreasing from cathode to anode at a pressure of 0.6 Pascal, gives something very different. The discharge is no longer uniform in the azimuthal direction. There is a strong azimuthal modulation of the plasma density, electric potential and electron temperature. This looks very much like the spoke observed in the experiment. This non-uniformity is moving in the -E cross B like in the experiment. We can put a probe in the model as in the experiment and measure the density, electron temperature, and potential as a function of time. We obtain something very similar to the experiment with large oscillations of the plasma density and sharp increase of the electron temperature, and plasma potential when the spoke reaches the probe. It is interesting to look at the evolution of the instability as a function of time from the beginning. We see the formation of the instability. It first moves in the +E cross B direction, with a large number of modes. This instability is predicted by the theory and is called the Simon-Hoe instability. It appears when the electric field and the electron density gradient are in the same direction, which is the case here. This can be seen from the linearization of the fluid equations and is described for example in these papers. Then, the number of modes decreases, and the wavelength increases until there is only one mode or one spoke. After some time, the spoke changes direction and moves in the -E cross B direction. The spoke has become an ionization wave. The electron temperature is much larger in the spoke's front and the plasma moves in the direction of larger ionization. The theory cannot predict and cannot explain the saturation of the instability and the change in the direction of the spoke that we see here. The fact that the electron temperature and ionization rate exhibit a large increase at the leading edge of the spoke is especially difficult to understand. To understand this, we must look at the mechanisms of electron heating. Electron heating in the energy equation is J.E, electron current density. Electric field. The electron heating per electron in electron volt per second is theta equals V.E. The electric field is perpendicular to the equipotential lines and is represented by the red arrow at this point here. The electron mean velocity has several components. A large component is the E cross B velocity perpendicular to E and to B. This velocity is perpendicular to the electric field, so the electron does not gain energy when it moves in the E cross B direction. Another component of the velocity is parallel to the electric field. This velocity is proportional to the collision frequency and inversely proportional to the square of the magnetic field. This velocity is small because of the low pressure and large magnetic field. There is a non-zero energy gain associated with this velocity. This is collisional heating, but this collisional heating is too small to explain the large electron temperature that we have in the spoke front. Now there is a third component of the electron mean velocity. This velocity is associated with the gradient of magnetic field. This velocity is well known in plasma physics and is proportional to B cross grad B. I will call it the grad B drift velocity. Since B is perpendicular to the simulation domain and grad B is horizontal, B cross grad B is directed downward. The grad B drift velocity is shown here in purple. We see that the electron heating associated with this velocity at this location, -V grad B.E, is positive. So, there is an electron heating due to this velocity. Theta is positive, so there is heating of the electron on the leading edge of the spoke here, but there is cooling on the other side here because of the change in the sign of the scalar product between the grad B drift velocity and the electric field. So, there is heating on one side, cooling on the other side. But the heating in the spoke's front here increases the electron mean energy and leads to ionization. This the reason why there is this sharp increase of the electron mean energy in the spoke front. The fact that ionization is larger on the upper side of the spoke is responsible for the upward motion of the spoke, in the -E cross B direction. The spoke is therefore an ionization wave in these conditions. This is a 2D plot of the electron heating and cooling theta, due to the grad B drift velocity. We see a large heating in the leading edge of the spoke and a cooling on the trailing edge. The heating due to the grad B velocity can be compared with the collisional heating associated with the component of the electron velocity parallel to the electric field. And we see that grad B heating is largely dominant on the front. We can also deduce from the particle simulation the electron energy distribution function around the spoke's front. We see the very large increase of the tail of the distribution that is very comparable to the experimental measurements. These two examples, the positive column striations and the magnetron discharge, illustrate the fact that particle simulations, or modeling in general, can often reproduce at least qualitatively some experimental features, but we need a very careful analysis of the results to understand the physics behind these results. In the case of the magnetron discharge, it took me several weeks to understand that electron heating was due to the grad B velocity. Here is a short conclusion. Our field of low-temperature plasmas is very alive. There are well-established as well as very promising applications. There are fascinating examples of nonlinear phenomena, complexity, and self-organization in low-temperature plasmas. There are still a lot of very basic physics questions. And the challenges are to develop more complex detailed models to understand physics, as well as to build more global and phenomenological models with predictive capabilities and which can be based on essential physics, combined with big data and machine learning. Thank you for your attention.